The thrust vectoring was originally thought to provide airplanes with the ability to take off and land vertically, but then it was also investigated to make maneuvers that could be used in combat and that other conventional aircraft could not do. Welcome to a new video where I'm going to try to explain how thrust vectoring works, and I'm going to tell you a little about the history and development of these systems. My name is Marcos, and this is World of Aviation. If you look up the definition of thrust vectoring, you're going to find this. The ability of an aircraft or other vehicle to direct the thrust from its engines in a direction other than parallel to the vehicle's longitudinal axis. Let's take a look. This is the longitudinal axis of the aircraft. And another important concept is the center of gravity. We could easily understand the center of gravity if we imagine hanging an airplane from this point. It would be suspended in perfect balance. We're going to start looking at it with something a bit simpler like this R-73 missile, which could also be any type of rocket, but this missile has exhaust gas orientation. This is its longitudinal axis, and the center of gravity passes through this. Let's remember Newton's third law. For every action there is an equal and opposite reaction. The thrust, which at this moment is pointing towards the center of gravity, generates a null moment, that is, there is no rotational force around this point. We can generate a deviation of the axis by changing the angle of the thrust force, generating a torque. One of the first methods of thrust vectoring in rocket engines was to place paddles in the engine's exhaust jet. The German B-2 missiles from the Second World War used this system. In contrast, more recent liquid propulsion rockets move the entire combustion chamber and the outer bell of the engine. Returning to airplanes, while we are going to see how it is used for super maneuverability, the technique was originally thought to provide vertical upward thrust as a way to give an airplane the ability to take off and land vertically or shortly, which is commonly called vertical takeoff and landing and short takeoff and landing, acronyms that mean vertical takeoff and landing, and the second short takeoff and landing. The idea is to divert the thrust about 90 degrees downward to generate the necessary force to lift the aircraft upward. The mechanical complexities of this design have been quite problematic, and there are numerous examples of different nations trying to develop aircraft with these characteristics. In the 60s, many test designs emerged with vertical takeoff and landing capability, but the only truly successful one from this era that ended up being mass-produced was the first generation of the Harrier series from Hawker Siddeley, and later British Aerospace Company. Having as much success as a carrier-based aircraft, the United States also improved it, giving rise to the AV-8B Harrier II built by McDonnell Douglas. All of these had as a precursor the experimental demonstrator Hawker Siddeley P-1127, which first flew in November 1960. In Germany, Dornier was experimenting with the Do-31, a fighter bomber and tactical support aircraft. Entwicklungsring Süd-BJ-101, a supersonic interceptor, intended to be the successor to the German F-104GB starfighter and the fighter bomber BAK-191B, a concept similar to the Harrier. All of these prototypes that were later cancelled due to their high development costs. In France, one of the attempts was the Dassault Balzac, a derivative of the Mirage 3, which had 8 small turbojets incorporated into the fuselage in addition to the main engine. This one lacked vector thrust but deserves a mention. Both the Germans, the British and the French responded to a North Atlantic Treaty Organization request to have a balanced takeoff and landing jet fighter in the 60s. On the Soviet Union side, we have the Yakovlev Yak-36, making its first flight in '63. It was a demonstrator of this type of technology, then applied in the Yak-38, a carrier-based aircraft that did go into production. The Yak-41 or 141 was another development, but this time of a supersonic aircraft of which 4 prototypes were manufactured. In the United States, many other very different concepts were tested, and some of them had vector thrust, like the Bell X-14 of the year 1957, the Curious Ryan. Up to the most modern Boeing X-32 and the well-known F-35 version B. And in relation to vector thrust boards for super maneuverability, these have an advantage as more normal aircraft only have conventional control surfaces such as ailerons and depth rudder. There have also been many developments in this technology, and I will only name a few. I also want to tell you that there are 2 types, the so-called 2D, with nozzles adjustable in 2 dimensions in the pitch axis, apart from the longitudinal thrust axis. These simply divert the exhaust gases up or down, like the F-15 maneuver demonstrators and the X-32 prototype, which may have later led to the F-22 Raptor, all of these American. Another type are the 3D nozzles, or nozzles adjustable in 3 dimensions in the pitch and yaw axis, apart from the longitudinal thrust axis. These divert the exhaust gases up and down, as well as to the sides. Examples of these are the Rockwell Messerschmitt Bulkov-Blohm X-31, the F-15, F-16 and F-18 modified by National Aeronautics and Space Administration to study this concept. And the Russian planes Mikoyan MiG-29 or BT, precursors of the Sukhoi Su-35BM and Su-37, as well as the Su-57, among others. Note that while the principle is the same, there are different ways to vectorize the airflow. The ones from the X-31, the F-22 Raptor, or the one from the Su-35 are not the same. I hope you liked it. If so, leave a like and a comment. These videos take many days, many hours of work, so if you want to financially support this effort, you have the means, PayPal and Patreon to do it. Until a new delivery, this is World of Aviation. Thank you.